All right, so your nodal method assignment is due on Wednesday, and historically, I'd say about 20% of the students will accidentally apply the Hardy-Cross method, which you're going to learn today, to homework 4. And I hope that you won't make that mistake, because homework 4 is not a Hardy-Cross assignment. The two methods, like the Hardy-Cross method, really has nothing that can help you out. It's not that I'm like telling you shouldn't use it because it's too useful. It just doesn't apply for that. Alex?
On number 2, it says to use the nodal method, but it also says to find the R value.
Okay.
Okay, so use the nodal method.
Yep. Yeah, you can apply R values. R is just a way of aggregating together constants in the Darcy-Weisbach equation. So we'll talk a little bit about R today. But the nodal method has a friction loss estimate, and so does the Hardy-Cross method. And so the thing that they have in common is that R values can be applied for both. But the take-home message is basically don't use the Hardy-Cross method for homework 4 because it won't get you to where you need to be. Now, let me give you a little bit of guidance on this problem. And it sounds like some of you at least have already started working on that and thinking about the problem. The situation is you've got 4 pipes, and at junction A there's a reservoir, and the elevation of the water in that reservoir is 25 meters. And what you're meant to assume from that is that the head at A is 25 meters. And likewise, since there's a reservoir connected at B, that tells you that the head at B is 20 meters of head. So you know how much energy there is at A and B. What you don't know is the direction of flow, the quantity of flow, and the flow rate coming in and out of the reservoir. So we don't know how much is going through the pipe, and for that matter, we don't know if the water's going from A towards C or from C towards A. One thing we do know is, let me just do a quick sketch of the system on the board here. So we've got our reservoir connected to junction A. Okay, we do know that the water is going towards junction A from the reservoir. Why do we know that? Well, because it's going to go from this tank towards this other one, from high head to low head. So the water is going into junction A from the reservoir. We don't know, is it going like this? Maybe. Is it going like this? Could be. Or it could be up towards A and away from A at the side. The one thing that we do know is it's not that. How do we know that it's not from C towards A and from D towards A? There's no outflow. Very good. Yeah, continuity would be violated. We can't have flow in but no flow out. So we're going to be using the continuity principle at each of the junctions, or at each of the nodes, as one of our primary constraints. So we just have to assume some flows. But what we know is that the flow is out of the reservoir at A towards junction A, and it's in to the reservoir at junction B. So we just have to start by assuming some flow direction. So let's assume, for example, as a first guess, maybe the water's going from C towards A and then from A towards D. So continuity is potentially valid at A. We have some place for the water to go out. Same thing at junction D. There's flow in, there's flow out. At junction B, flow in, flow out. So junction C, likewise, there's flow in from that external 0.2 cubic meters per second. It looks like in this hypothetical it would be split 2 different directions. So we assume some flow direction, and continuity must be satisfied. And now let's go back to this idea that I mentioned earlier, that we know the head at A is 25 meters. So head at A is 25 meters. what is the head at C? According to this first guess of flow direction, head at C is what? Well, it's at least the head at A, because if the water's flowing from C towards A, that means there's less energy at A than there is at C. So the water wouldn't be flowing from C to A unless C had more head. So according to this assumption, we're going to say the head at C is the head at A plus the losses through pipe AC. All right. Now, let's see. What do we know about the head at B? The head at B is 20 meters. And what do we know about the head at C in terms of the head at B? According to this flow direction, we know that the head at C is the head at B plus the head loss through pipe BC. Okay? So now we can relate these two equations because they're both saying the head at C is something. Okay, so if I relate those two together, then I'm saying the head at C is equal to the head at C. So the head at A, 25 meters, plus the head loss through pipe AC. Well, we can say that the head loss through pipe AC is R times the flow rate through pipe AC. And R is just the friction factor times the length of the pipe divided by 2G A squared times D. So these are going to be constant, relatively speaking. F value will change a little bit depending on the flow rate. But aside from that, R value is relatively constant once we get past the first iteration. So we could say, if we want to say that the head at C is equal to the head at C, then one side of that expression is 25 meters plus the head loss through pipe AC. So that is the R value for AC, and then times the flow rate through pipe AC squared. Okay, so that's one side of the equation is equal to 20, because now the other side of the equation was the head at B, 20 plus RQ BC squared, and that's the R value for pipe BC. All right, so we know from this a relationship of QAC in terms of QBC. You know, R is going to be some value that you can calculate for both AC and BC. And then the other thing we know about this junction here at C is continuity. We know that QBC plus QAC is equal to 0.2 cubic meters per second. So we've got two equations and two unknowns, which means we can solve for either QAC or QBC and then substitute it into this and find the other one. So all of that depends on whether our guess was correct. And if our guess, like if you end up going through those calculations and you get that the flow rate is negative, then that tells you may need to adjust your assumed flow direction and recalculate again. So if you get a real and positive solution to this series of two equations, two unknowns, then your first guess of flow direction was correct. Okay, so that's all the hints I want to give you for now on that one. But I think it's a pretty good step in the right direction for thinking through how do you find out the flow rates. And you could do the same thing at junction D. You can say the head at D is the head at B minus, because you know if the flow is going from B towards D, then the head at D here is the head at B minus the losses. And the same thing from here. It's the head at A, 25, minus the losses, which is going to be R times Q squared. All right. So you've still got some additional time to think through those problems. Now, moving on from the nodal method to the loop method, sometimes also called the Hardy-Cross method. It's for situations where we've got more than just one or two junctions. When we've got a complex network and there is flow that is otherwise, it's going to be unclear how much of the flow goes through each of the pipes. It's kind of an indeterminate flow. Because if you look at flow coming into this complex network and the flow going out, it could go through this top series of pipes to migrate towards the outlet. It could go through this middle one or this middle one or the bottom route. There's so many different routes through all of those different pipes to get from one point to another. Think about what you learned last time, though. What can we say about the amount of energy loss that occurs regardless of the route that it takes from the inlet to the outlet? If it goes through this top route, how does the energy loss compare to the fraction of the flow that's going through the bottom route? It's the same. That same principle applies in the Hardy-Cross method. And the whole essence of this method is trying to balance what flow rate would it take so that we have the same head loss through each route that the water could potentially go through. So it's going to be a series of complex adjustments, corrections, with the overarching goal to have it so that we're calculating the flow rate that would bring balance so that regardless of which route the water is taking, it has the same amount of energy loss. That's kind of what's working in the background of this method that you're going to learn today. We're going to have to do a lot of iterations. And so you can either set that up by hand, and it's very time consuming, or if you set it up in a spreadsheet, it's a little bit, I don't know, it's a little bit fun entering the equations the first time, and then you can just copy and paste. If you have it set up with relative references, then subsequent iterations are no problem at all. Computerized techniques like water gems, which you're going to learn to use later this semester, it uses this method. That's what's running in the background. And I think it's important to understand how these sophisticated design tools actually work and what their assumptions are. So we won't do it by hand. I used to have students do this by hand, but we'll jump right into the spreadsheet part. And I think with the spreadsheet, you'll have a good idea of kind of the balancing act that has to be done to come up with the flow rates. And then it'll really make you appreciate when you do use water gems, how simple they make it. So this is all about balancing the flow so that you have the same head loss regardless of route between 2 points. Any questions so far? All right, so head loss is going to be some R value times the flow rate, and then the N value that is here depends on the friction loss method that you're using. If you're using Darcy-Weisbach equation to estimate your head loss due to pipe friction, then you'd use 2 as the exponent. In the Hazen-Williams equation for friction loss, then you'd use 1.85 as your exponent in that N value. But you have to calculate an R value, which is all of these terms that are aggregated together, the constants like the pipe diameter, the friction factor, the length of the pipe, and so on. And we usually just only take into account the head loss due to pipe friction, and we typically are going to neglect the local losses when we're setting this up on a spreadsheet. The design tools like Bentley's water gems, you can put in the local losses, and it doesn't complicate things too much when you're using that. But if for our purposes in the example that we will work today and on Monday, it's just going to be only friction losses that we take into account. So the R value here, if we're using the Darcy-Weisbach friction method, you'll see, again, we went over this on a previous slide, it's the friction factor, which varies depending on Q, and then it's the length of the pipe, and then the denominator 2G, the cross-sectional area of the pipe squared times the diameter. So just to teach you the technique of this method, we're going to solve our first example with a fixed R value. But then on Monday, you're going to calculate R values yourself and they'll be dynamically updated as our solution gets closer to converging. The F value is going to change a little bit, and so you'll notice that for each iteration, we'll have slightly different R values. But just for today's kind of baby steps towards learning this method, we'll look at an example with a fixed R value. Now, how do we calculate an R value? Well, let's say, for instance, that we've got a certain known flow rate going through a pipe. So if the flow rate is known and the diameter is known, that's going to enable you to calculate the velocity, which will enable you to calculate the Reynolds number. And if we know the material of the pipe, here in this example it's saying concrete, where we have some equivalent sand roughness that's known, and the diameter of the pipe, then that defines both of the terms here in the Jane equation. So just to save some time for us to spend more in the spreadsheet, if we wanted to calculate the R value, you'll notice here I've determined the cross-sectional area, from that the velocity, with the kinematic viscosity of water and the velocity and the diameter, we get a Reynolds number. So this is just applying the Jane equation to find F, and then once we have the F value and the other constants, the R value is, I don't know, I guess it does have units, because we're going to multiply R times Q squared, and we will get diameter out of that. But remember that the Darcy-Weisbach equation itself is not dimensionally homogeneous. So that's why here, once we've calculated R, I don't bother to keep track of the units, because when we put it into the Darcy-Weisbach equation, when we apply it by multiplying Q squared times R, we're going to get units of length on the left-hand side. We don't have units of length on the right-hand side because this formula is not dimensionally homogeneous. So it's just applying the Jane equation and then putting it in with the rest of the constants. So that's R. So let's say that we've got a certain network that we want to find out how much flow is going through each of these pipes. So in this situation, water's coming in at one junction, and on the handout, second page, I think I've labeled the junctions. I think I've called this top left one junction 1, and then this is junction 2, where the flow of 50 is coming out. Junction 3 is the bottom right, where 30 is coming out, and junction 4 is where the 100 is coming in. So we're going to name each pipe by their junction. So for instance, this is pipe 1, 2. Pipe 1, 2 starts at junction 1, ends at junction 2. We don't know how much flow is going through that pipe or even what direction it's going through. So there's some initial questions we have to ask ourselves anytime we begin a loop analysis or applying the Hardy-Cross method. The first is, for the pipe network you've got, how many loops are there? And for this one, that's an easy question. You can see that there's 2 loops. But in the case of a network that's a little bit more complicated, like this network, that's not going to be as simple. You'd have to count up each loop individually and be aware of that, because each loop is going to have its own set of calculations. So here there's 2 loops. The N value that is going to be used in this formula that's here boxed in blue, N refers to the friction loss coefficient. For us, if we're using Hayes and Williams, it's 1.85. For Darcy-Weisbach, it's 2. We're going to use 2 for our example today and on Monday, because we're going to use the Darcy-Weisbach friction factor. So N is 2 for our purposes. Now define a direction. What I mean by that is we're going to assume that clockwise is positive. So we're going to label the loops. And in the handout, you can see that this lower loop I've called loop 1, and the upper loop is loop 2. So our defined direction is that any flow that is going along with clockwise would be considered a positive flow. I brought in a marker today. Oh, here it is. All right. So I'm just drawing this on the board. It's 1, 2, 3, and 4. Clockwise is positive. So what that means is, like if the water's going from 1 towards 2, then that's a positive flow. We're going to keep track of the magnitude of the flow and also its direction. So if it's going along with this clockwise direction, then we're going to put a plus flow rate into these formulas. But if the flow is going this way, that's going to be a negative flow rate, because this is opposite to the clockwise. You can see the clockwise presumes that the flow would be going from 2 towards 3, but this is against that clockwise flow direction. So we have to assign guess flow rates. So let me show you what I mean by that. The flow is coming in at 4. Well, that's not very good. That's a little better. The flow is coming in at 4, out at 1, out at 2, and out at 3. So we've got 30 coming out here, 50 coming out at 2, 20 is coming out at 1, and then 100 units of flow are coming in at 4. So I'm going to assume that the water goes like this and like that, and I've already drawn that one, so I'll leave that there. So it goes up here, then there. It's going to go up through there, and then I'll just assume that the flow is going this way. Okay, now if those are the flow directions that I'm assuming, I have to come up with an initial guess of what the flow rates are. So, 100 comes in, it could be 30 and 70 as my initial guess. Or I could say 99 and 1. As long as at every junction continuity is honored, then it's okay. It'll eventually get where it needs to be. It'll eventually balance out, as long as at each of the junctions we have continuity honored. So let me just show you what that would look like. So I'll do 60-40. Okay, so I've got 40 that went this way and 60 that's going up. Okay, so if I've got let me do this one. I've got 40 coming over and 30 going out. That means that I've got 10 left over, right? Because so far 40 in, 30 out. So I'll say it's 5 and 5. So if 5 is coming into 2, that means that this must be 45. Okay, now let's look at this junction. We've got 65 coming in and 65 going out. So at each of the junctions, continuity holds. So in and out are equal at each of the junctions. I could have done the same thing with different flow rates. And I'm going to ask you to come up with your own flow rates. So this is an important thing that a lot of students struggle with, is practicing that first guess flow rates. But just to walk you through the rest of this procedure, once we've assigned the guess flow rates and calculated R values, or if they're given, like this first example, then we calculate this numerator term, and I'll show you how we do this on the spreadsheet. R times Q times the absolute value of Q for each pipe. And then you calculate N times R times absolute value of Q. Now, why are we doing absolute value? Because some of the flow rates are going to be positive, some are going to be negative, and if we want to retain that sign, then Q times absolute value of Q will retain whether the flow is against the clockwise or with the clockwise. And then there's this minus sign here. So this delta Q is a correction factor that helps us get closer to the correct flow rates. So this formula is balancing out the friction losses. Remember how I said that each route in the network has to have the same amount of head loss regardless of which way the water goes through there? We want to find out what flow rate makes it so that all the head loss amounts are the same. Somehow, it's because it's been set up that way, this formula calculates that and adjusts based on the deviation from what flow rate would give you the appropriate amount of head loss that causes the same head loss through every route. So let me show you how this works. We've got this example, and let me pause for a moment while you do your first guess of the flow rates. So similar to what I did on the whiteboard, I'd like you to, there on the paper that I've given you, on your handout, you've got 100 units coming in at 4, split it. You know, you could do 98 and 2, you could do 70, 30, whatever you like. 50, 50, that's kind of boring. Do whatever you want, and make sure that at each junction, in and out are equal.
So it doesn't matter the clockwise rotation?
Yeah.
Positives and negatives don't matter right now?
Nope, not for assigning the flow rates. But draw an arrow direction, and then next to it, a number. So you're assigning both the direction of flow and the magnitude. Up at the same answer. So don't just think like this is somehow the right answer. It's not. It's just what I went with. Okay, so once you've got the flow defined, be sure that you do this. You write which loop is loop. Here's loop 1. And a little reminder that this is clockwise, positive. Here's loop 2. Clockwise is positive. And let's start up Excel. I emailed you a template file. It's also posted on Blackboard if you want to get it there. So it is the Hardy Cross example student start file. We'll use example 1 for today. And I don't know, maybe just to make things easier later on, it would be worth drawing your flow direction and the flow amounts. I mean, I guess you can glance at the paper. Why is this not showing up very good? I guess that's good. So for me, I had, that's not good. 25 with that one. It's going to be 25 for this one. 25, 30, and 70. Oop. Okay. So let me. If you don't want to do all this sketching of the flow directions in your spreadsheet, that's okay. I'm just being fussy because I want people who are watching the video to be able to know what I had sketched out on the whiteboard. We got a couple of people who are missing class today because they're running in an indoor track meet in Louisville. Brett and Kent. They're running. All right. So, yeah. Does my continuity match? It didn't at first. Did anybody else notice that I accidentally had written 70 here for a second?
Yeah.
Yeah. Speak up when I make mistakes.
You were.
We
saw you rubbing the beard.
Yeah, I was, something doesn't look right here. I got there eventually.
Well, you first said that this isn't like the one we're doing. I thought you were doing a different problem until you
Yeah.
changed.
That's all part of the master plan. I never make mistakes. It was just all part of the... No, I make plenty of mistakes. All right. So does anybody have questions before we start applying the method? Okay, we're starting with iteration 1. So type in the number 1 here for iteration. We're going to be starting on loop 1 calculations. And let's type in the details for pipe 1-3. I'm going to put, by the way, I think I got to have a quotation mark, 1-3. Because if you just put the 1 minus the 3, I'm not sure if it'll work. 1 minus 4. Yeah, let's say January 4th. That's what it is. So this little quotation 1-4, quotation 3-4. So we're going to put in the details for these pipes. We're using the Darcy-Weisbach friction factor, so N is 2. Our R values are given and fixed for this problem. Monday's example, they'll be dynamically updated. But we're just going to assume that it's constant here. So 3, 6, 5. Okay. Now let's put in the details. I'm going to put in my flow rates. You put in yours. Because it really will work regardless of what the starting thing is. So for me, it's 25 is the flow rate through pipe 1-3. Because it's in the direction of flow, so positive 25. Now what about 1-4? It's in the same direction that I'm assuming is positive, so I'm going to put in 70. But here in pipe 3-4, so pipe 3-4, it's going against the clockwise direction. So I'll type in minus 30 for the flow quantity there. Alex, do you have a question?
For your loop, oh, never mind.
Okay. It would have made more sense if I had the top one called looped 1.
That's
Yeah.
what
Yeah.
exactly.
It's like, why? Yeah. I don't know. Now, R times Q times absolute value of Q. So we're going to put in a formula here. So equals R times Q times ABS of Q. Now, I've got the formula centered, so I can't click on that cell location anymore. So I just have to type in F14 because I can't click on it since I've got the centering. All right, so it's R times Q times absolute value of Q. Okay, so 1875, and I'm going to drag that down for the other 2 rows in this loop. All right. Now I'm going to do N times R times absolute value of Q. So equals N times R times ABS of the flow rate. Okay. And I'll drag that down as well. Okay. Now I need to take the sum. If we look back to this formula, this is the formula that I'm going to be applying. Let me paste it here. So I need to know the sum of these 3 things within this loop. So here I'm going to do equals sum, and then I'm going to highlight the 3 cells above it. Boy, it's nice that it's italiced already. And then for the one, this, I'm going to do the sum of these ones as well, equals sum of these 3. Okay. Good. Marshall, do you have a question?
Nah,
Okay.
sorry.
Anyone?
What about equals 0
One of the sums does, or one of the?
for the sum?
I may have an error. Nothing's impossible, but you may have an error if it equals 0.
You guessed it perfectly.
No, that was just weird.
Okay, all right. So now, the delta Q is this formula. Okay, so here it's equals negative of this divided by that. Okay? We're going to type that formula in again. We're not going to just use anchoring and drag it down. We want it to be able to be dynamic, so I'm going to type it in again. Equals negative this divided by that. Equals negative this divided by that. By typing it in these 3 times, I'm going to be able to copy this whole block and paste it down. And so my subsequent iterations will automatically calculate this correction factor. Okay, so I've got this delta Q. So the corrected flow rate, once you've got the delta Q, your corrected flow rate is your original guess flow rate plus the correction factor. So this delta Q is telling us, well, the head loss, it's not where it needs to be. If you adjust these flow rates, you'll be closer to this state of equal head loss regardless of route. So these corrected flow rates are a little bit better. All right. Any questions about iteration 1, loop 1? Because next what we're going to do is, we're still in our first iteration, but we're going to analyze loop 2. Okay, so in loop 2, we've got pipe 1-2. We've got pipe 2-3 and pipe 1-3. Those are our 3 pipes. And we can enter in the N values, are just 2 for all of them, and transcribe the R values. So I think it's 1 for pipe 1, 2, and the R value is 2 for pipe 2, 3. R value is 3 for pipe 1, 3. All right. What was my guess for pipe 1, 2? My initial guess was 25. Okay. My initial guess for pipe 2, 3, I have to put negative 25 because it's opposite the clockwise direction. So negative 25. Pipe 1, 3 is a very special pipe. It's a very special pipe because it's the one that is shared by both loop 1 and loop 2. So we have to treat it in a special way. I'm not just going to put in my initial guess for that pipe. Like my initial guess was 25, right? Well, that's old news. I've got a better guess for that now. I've got this guess. See, pipe 1, 3 is in the first iteration, and it's also, well, the first loop, and it's also in the second loop. I'm going to bold it just to draw attention to the fact that it's in both of the loops. So this is the one I need to be a little careful with, this common pipe. Okay, so I'm going to say the flow rate, I'm going to use this updated value. But I'm not going to say it's 4.244 because when we did the correction, from the perspective of loop 1, it's saying now that the corrected value is 4.24. What does that look like when you're standing in loop 2?
Negative.
Negative, because now it's against our clockwise flow direction. So I'm going to say equals minus, and then click on this cell location. Okay, so the rule that you should apply is always use the latest updated flow rate that you've got for any pipe. Don't go back to these original guesses if you've got something better. Okay, so now let's apply this formula of R times Q times absolute value of Q. And drag that down through all 3 of them. And I guess I'll center it and reduce the digits here. Okay, N times R times absolute value of Q. And now I need to find the sums. And once we've got the sum of one column and the sum of the other column, we can calculate the delta Q. So delta Q is equals minus this one divided by that one. I'm going to repeat that. 1 divided by the other. And one last time. These look different, but they're not. It's just the amount of digits that has been displayed. And it's centered. There we go. It's the same. Okay, and then corrected Q is the original flow rate plus the correction. It's no coincidence that our delta Q is smaller in the second loop than it was in the first loop. We're already starting to see an improvement in our guesses of the flow rate. Any questions so far? All right, things are about to speed up. We're not going to have to type too many more equations in. Now we're going to start on our second iteration. So let me just type over here iteration 2. And aside from that, I'm going to copy all of these details about the system. So Control C. I'll just paste that, Control V. So all of the naming stays the same. The N values stay the same. And for this example, we're saying that the R values are the same. What you'll see on Monday is that when we have updated flow rates, that's going to change N, and N is one of the terms in R. So Monday's example is more complicated, but you're learning the technique today with these simpler assumptions. All right, so what about flow rate? What's our best guess of the flow rate at 1,3 at this stage? Well, I'm not going to refer back to this one because I've got an even better guess of 1,3 right here. So I'm going to say it's equals negative of the reference from the previous loop. Anytime you're referring to a flow rate in a different loop, you need to put the negative sign there because it flips the perspective of whether it's clockwise or anti-clockwise. So when I was looking at that pipe in loop 2, it was negative 0.37. Now here from the perspective of loop 1, the flow rate is positive 0.37. Okay? What's my best guess of pipe 1,4? Equals, here it is, this 49 one. Best guess of pipe 3,4, right there. Okay? Now I'm going to just highlight this entire block. Everything, all of the calculations from the first iteration, the first loop, Control C to copy. I'm going to paste it down here so that it calculates the R times Q times absolute value of Q, calculates the N times R times absolute value of Q. It sums up the three terms above it for both of those. It calculates the delta Q for each one and the updated flow rate. So evidence that things are headed in the right direction are correction factors getting smaller. That's good. And therefore, the flow rate guess through pipe 1,3, it's stabilizing. It's not changing as much. You know, initially we said 25, then 4. It's getting closer. The guess in and the guess out isn't changing as much. Okay, now let's do this second loop. So the flow rate through pipe 1, 2, where's our best guess of that? It's right here. Best guess of pipe 2, 3 is from the first iteration, but 1, 3 is that very special pipe which is shared in common between the two loops. So it's equals negative of this latest updated flow rate. Okay, and then I can copy this whole block of formulas, Control C and Control V. All right. So look at pipe 1, 2. Well, we started off by saying it's 25. After correction, well, it's 28.8. Now we're saying it's 29. It's not changing a lot. It's stabilizing. We're getting pretty close to convergence. But some of the pipes are still having some change, 1.1 to 1.5. We've only got 1 minute left, and that's all we need to finish this. You can copy the whole thing, all of it, Control-C, paste, Control-V, and the only thing I have to change is just the label. This is iteration 3. And if you look, the guess flow rate in and the guess flow rate out, these correction factors are getting minuscule. Look how small the change is. We're basically there. The solution has converged. If I copied and pasted this into a 4th iteration, just for laughs, the correction factor is 0. So now we know the actual flow rate through each of those pipes. And if you look from the perspective of the loop 1 or loop 2, it's the same flow rate, 1.512. And so the negative sign tells you whether it's clockwise or anti-clockwise, and we've got the magnitude of the flow rate. So each of you probably had different initial guesses, and if your spreadsheet's set up correctly, you'll have the same output flow rates. If not, there may be an error in your spreadsheet, and I'm happy to help you find it. But are there any concept questions? I've held you over. It's 1:51. So I owe you time now on Monday, and I'm going to pay it back with interest. Many of you I know are starting your weekend, so go do that now. All right. See you on Monday.